Let's add another concept from our science of work, the law of large numbers. What this law states, often referred to as the central limit theorem, is that no matter how skewed the variation is of independent samples within a population size, the mean of all samples from the same population will be approximately equal to the mean of the population, given a large enough sample size. And projects nearly always offer enough tasks and complexity. In simpler terms, the more samples you have, the more distribution looks like the standard bell curve we're all so familiar with. Question is, what does this do to help us with our goal of more throughput, less operating expense, less investment, greater agility, greater reliability, and better quality? Think about a single project and imagine we could plot the demand for a given resource type over time. On some days, demand is very low, and on others, very high. There's an average we can draw through this. If, however, we were to resource the project to the average level, we'd be unable to meet the peak demands and we'd fall behind on schedule. If, on the other hand, we were to resource up to peak demand for those few occasions when it's required, in most cases, we'd go broke paying the holding costs of the resources when they were not doing any value-adding work. Multiply this by the total number of projects in your program or portfolio, and pretty soon you're talking real money. You say, how about if we pool the resources? And that's a very good idea, to be sure. However, whilst necessary for the full solution, it's not sufficient. As we can see, the aggregate demand has far less variability than each individual project on its own. This means that as long as we know which is the priority task on the priority project, she'll be right. But priorities are so often set by the dog with the biggest bark, not necessarily the one with the fiercest bite. How do we make sure the resources we have are being used to optimum effect for the value creation engine as a whole? If we're going to have a complete solution, we need a valid signal based on criteria of sound, reason, and logic for the assignment of a given resource to perform the work on a particular task. How can we systematically go about delivering our projects earlier than we would otherwise think reasonable and possible? We'll save costs by reducing burn. We'll get our benefits sooner by completing earlier. And we'll be able to move on to the next big idea before our competition catches us. What does the law of large numbers have to teach us about completing projects on time, in less time, every time? First, we need to understand something about uncertainty in schedules. Let's imagine you were asked to estimate how long it would take you to ride 10 kilometers. Your answer would no doubt be, it depends. What's the terrain like? How heavy is the traffic? How fit am I? Is it a race? What kind of bike will I be riding? And a host of other factors. To keep it simple, let's say there are 3 parts to the 30-kilometer track: downhill, level, and uphill. Let's say that in the downhill section, you can do the 10 kilometers in 20 minutes. On the level, you take 30 minutes. And when you're going uphill, it's 60 minutes. Now, let's think of you completing 1,000 rides of 10 kilometers. And for each one, you note the time it took you to complete the course. For each ride, you plot how long does it take to complete. Then you end up with a plot that looks something like what you see on the screen. 10% of your rides were downhill, and you can complete them in 10 minutes or less, the P10 estimate. 50% of your rides were either downhill or on the level, and so you could complete them in 30 minutes or less, the P50 estimate. 90% of your rides were downhill, on the level, or uphill, and thus could be completed in the 60 minutes or less in the P90 estimate. Now, If you are asked how long will you take to complete a 10-kilometer ride, what would you answer? What if you knew what the probability curve was like as you see in front of you, but you were told that as long as you estimated within reason, that estimate would be accepted? But once that estimate was accepted, there was a big penalty if you finished late. If you're anything like the rest of us, you'll likely opt for the P90 and keep whatever contingency you can get up your sleeve, just in case you end up drawing the short straw and having to ride uphill the whole way. TOC, with its counterintuitive thinking, goes the other way, understanding that if we collect up all the contingency each individual has stashed away for themselves, we can take advantage of the law of large numbers. The whole is better than the sum of its parts. In practical terms, a P50 estimate equates to the touch time of doing the work. No waiting around for someone else to finish. You're fully kitted and ready to go just in time. Everything and everyone you need are at the start line. And you're left alone to do the work without any interruptions. Imagine then being able to scoop up all the differences between the P50s and the P90s, and rather than hoarding it for yourself at the task level, making it available to the project as a whole. Let's look at a 100-day schedule made up of 5 tasks, each of which is 20 days. And let's say, for argument's sake, that the P50 estimate is 10 days for each task. By the law of large numbers, all of my wildly varied distribution curves, when aggregated, take on the shape of the famous bell curve of the normal distribution. It's the central limit theorem in action again. And because a normal distribution is evenly split down the middle, we can make a good enough rule of thumb that the proper sizing of the buffer is equal to half the duration of the chain feeding into it. Thus, my 100-day project becomes a 75-day project, in theory. But as a client once said to me, theory is the dinner jacket you take off when your car gets a puncture. What happens in practice? Let's take a look at this somewhat more complex scenario. I have 2 work streams running in parallel. Based on tracing the longest path of dependent events, known as the critical path, we get to a total duration of 84 days. Note in workstream 2 that task 3 can start early or late. We'll come back to this in a short while, but first let's see what happens when we add resources to the model. In this scenario, we have shown task 1 and task 4 as both requiring blue resource A. This blue resource cannot be in 2 places at once. One way or another, we have to resolve the contention, either by adding additional blue resources or by stretching out the due date of the project. If, in this example, we resolve the contention by allowing task 4 to start only once task 1 is completed, we've caused our project duration to extend from 84 to 100 days. In addition, we've added more slack into the schedule, meaning both task 2 and task 3 have a chance of starting early or late. The usual inclination is to start early, as it gives the hope that risk will be mitigated. However, there is significant risk associated with flooding the engine with work in process. How many open work fronts can you effectively manage? But if everything starts as late as possible, then everything is on the critical path. And a delay anywhere is a delay to the whole project. How do we get back on track to our goal of delivering more throughput at lower cost with greater speed, reliability, and quality? Let's go back to our concept of the P50 estimate and reduce each of the tasks accordingly. Then let's introduce a project buffer. This buffer is the equivalent of a shock absorber at the end of the resource-leveled critical path. Most people don't trust schedules as they are brittle. As soon as something goes wrong, a shock, the schedule can no longer be relied on to provide a valid signal as to where to focus. Putting this shock absorber in place means we can have a stable schedule capable of absorbing any regular uncertainties Murphy brings to the project. The buffer is made up of the sum of the differences between the P50 and P90 tasks. In practical terms, a useful rule of thumb is to make the buffer equal to half as long as the tasks which feed it. And remember that every task is sized according to what the best guess of the touch time effort will be. Put another way, the buffer should be equal to a third of the critical chain. The combination of the resource level critical path and the project buffer make up what we now call the critical chain. In a similar way to how we added the shock absorber of the project buffer to the critical chain, we add the shock absorber of the feeding buffers to those feeding chains which connect into the critical chain. The rule of thumb is then to start feeding chains as late as possible in order not to flood the engine with an excess of WIP, but not so late that everything on the feeding chain becomes part of the critical chain. In the next session, we'll see how these buffers play a crucial role in signaling where to focus. Note, a feeding buffer is not the same as slack. Slack implies protection that isn't needed and may be eliminated. A feeding buffer is an integral and critical part of ensuring the stability of the schedule and being able to cope with inevitable uncertainty.